Get started. What is an acid? Does anyone know? So a substance that acts as a proton donor is called an acid. And what is a base? A substance that acts as a proton acceptor. Okay, and these are some examples of a few acids and their corresponding bases. So in case of your HCl is an acid, and what is the base? Any ion which will accept hydrogen ion. Okay, any substance which will accept the hydrogen proton. And then there's also the example of H2CO3, okay, which splits into H plus ion and HCO3 or your bicarbonate. What are alkalis? So these are metallic hydroxides, for example, sodium hydroxide or potassium hydroxide, and these satisfy the criteria of bases, but they dissociate to form metallic ion and hydroxyl, which being bases accept the hydrogen ion, right? So alkalis are considered as bases, okay? Now there's a term called a strong acid and strong base, or a weak acid or a weak base. Let's try to understand what that means. So an acid or base having a strong tendency to dissociate into ions is called a strong acid or a strong base, and an acid or base having weak tendency to dissociate into ions would be called a weak acid or a weak base. So your strong acid has a weak base, while a weak acid will have a strong base. Okay. Now, for example, a strong acid such as hydrochloric acid, it has a weak base, as I showed you earlier, which is chloride ion. And a weak acid such as HCN has a strong base that is of cyanide ion. Okay. Now, what are ampholytes? Ampholytes are substances that can act both as acids and bases. And what is the most common ampholyte that we come across? Water, right? Now, a word about pH and hydrogen ion concentration, because that's what the whole acid base unit is about. So, acidic or the basic nature of any solution is measured by the H ion concentration. Now, since the concentration of hydrogen ions in biological fluids is quite low, so conventional units such as milliequivalent per liter or moles per liter is not commonly used to express hydrogen concentration. So the most appropriate term to express hydrogen ion concentration is pH. Okay, what is pH? pH is defined as the negative logarithm of hydrogen concentration. Okay, and pH is equal to minus log and H plus ions in brackets. Okay, it's important that we know that pH and hydrogen ions are inversely related. Okay, and hydrogen ion concentration of 150, for example, 150 milliequivalent per liter will be 0.8. Okay. Now, what is neutral pH? What is acidic pH? And what is alkaline pH? So pure water has an equal concentration of hydrogen ions and hydroxyl ions, which is around 10 to 7 moles each. So pure water has a pH of 7, which is considered neutral. Now solutions with pH less than 7 are considered acidic, and those with pH more than 7 are considered alkaline. the hydrogen ion concentration and pH of biological fluids, okay, is given in this table, as you can see on the right, just to give you an idea. Now, about maintenance of blood pH. Now, whenever we refer to the term blood pH, we always mean the plasma pH. Okay, so the normal plasma pH is 7.4. All right, and that means that at a normal plasma pH of 7.4, the hydrogen ion concentration is around 40 milliequivalent per liter, which is higher than the intracellular pH of a RBC. That would be 7.2. Now, the plasma pH is compatible with life and it varies from 7.7 to 6.9. At rest, a normal pH of mixed venous blood is 7.38 compared with 7.41 of arterial blood. Why is that so? Because of the uptake of carbon dioxide by blood as it perfuses the tissues. Now, normally the pH of ECF is maintained within a narrow range of 7.35 and 7.45. Now, how are the acids produced in our body? So, there are acids which are mainly produced by the body due to metabolic activities, and some are produced through our diet consumption. Okay, so now the daily consumed diet, it contains many acids and alkalis. And in addition to that, as I said, cellular metabolism also produces number of acidic and alkaline substances that have an impact on the body pH. Now, the metabolic activities of the body are accompanied by production of two types of acids. So this is important because you need to know what are volatile acids and what are non-volatile acids. So, carbon dioxide is a volatile acid which is produced from the aerobic metabolism of cells. It's also a major end product in the oxidation of carbohydrates, fats, and amino acids. Carbon dioxide accounts for over 12,000 milliequivalent per liter of hydrogen ions per day. Why is it considered an acid? Any thoughts? So, carbon dioxide is considered an acid because when it combines with water, which is a reaction that we already know is catalyzed by carbonic anhydrase, it forms a weak acid, that is H2CO3. And we know that that dissociates into hydrogen ion and bicarbonate ion by this reaction that you can see. CO2 plus H2O gives H2CO3, which dissociates into hydrogen and bicarb ion. So that is why carbon dioxide is called an acid. Why is it called volatile? Because it's a gas, okay? And under normal circumstances, almost all the carbon dioxide is excreted by lungs. Now let's go on to non-volatile acids, or also called as fixed acids. So they contribute to about 50 to 100 milliequivalent of hydrogen ions per day, and that depends on the diet. So which are the non-volatile acids? Sulfuric acid, phosphoric acid, hydrochloric acid, and organic acids like lactic acid, acetic acid, and beta-hydroxybutyric acid. Also, uric acid, which is produced in the metabolism of nucleoproteins, also comes under the category of non-volatile acids. Now, about the production of bases by the body. So, your bicarbonate ion is produced by metabolism of organic anions. For example, citrate, which offsets non-volatile acid production to some degree. Then ammonia is produced in the amino acid metabolism, which is converted into urea. And so again, its contribution as a base in the body is less. Now, what are the defenses in our body against changes in hydrogen ion concentration? So there are basically 3 lines of defense to regulate body's acid-base balance and maintain the blood pH around, as I said, 7.4. So this defense system is made by the buffer systems of body fluid. Okay, so the buffer systems form the first line of defense. They act instantaneously in the ECF, and they immediately combine with hydrogen ion to prevent changes in hydrogen ion concentration, and they form a temporary measure to control changes in hydrogen ion concentration. Second is your respiratory mechanism. Okay, this forms the second line of defense. It acts within a few minutes. It acts via respiratory center to regulate removal of carbon dioxide and in the process H2CO3 also. And it forms a short-term measure to regulate changes in the hydrogen ion concentration. Then third line of defense is your renal mechanism. This mechanism takes days or weeks to operate. It's slow, but most powerful and effective in regulating pH. It acts by reabsorbing filtered bicarbonate, generating new bicarbonate, and excreting hydrogen ion as titrable acid and ammonium ion. And so by all these measures, it provides a permanent solution to acid-base balance. So if you recall about the renal mechanism, we went through it in the last lecture where we studied about how there is filtered bicarb, how there is generation of new bicarb ion, how is hydrogen ion excreted as titrable acid and ammonium ion. So that all this part that we studied last time is part of the renal mechanism to regulate the acid-base balance. So very broadly, your respiratory mechanism is a quick mechanism, quick and short term, okay? But your renal mechanism takes a long time compared to the respiratory mechanism, but is very powerful and effective. So it's a long-term defense against the hydrogen ion changes. Now about the buffer system, which we just mentioned is the primary defense. So what is a buffer? A solution which consists of weak acid and its salt with strong base that prevents changes in pH when hydrogen ions are added or removed from it. So a buffer cannot remove hydrogen ions from body. It simply acts as a temporary shock absorbent to reduce free hydrogen ions. And hydrogen ions have to be ultimately eliminated by a renal mechanism. So again, buffers is a temporary shock absorber. It cannot remove the hydrogen ions. It can only reduce them, okay, temporarily until the renal mechanism acts. Now, when acid is added to the buffer solution, its hydrogen ion concentration is increased and the reaction is forced towards right, leading to an increase in undissociated molecules. So, increase in hydrogen concentration is less. When a base is added to a buffer, the reaction shifts towards left. So, what will happen now? More hydrogen ions are released from the buffer to combine with the base, and that will limit the decrease in hydrogen ion concentration. Now, this is a very important topic, and you need to know what is the Henderson-Hasselbalch equation. I would say the derivation to it is not as important from an exam point of view, but this is an equation that you need to know. And even if you ever get some values, you should be able to substitute them in the equation and work out the equation. So this is used to calculate a pH in a buffer system, okay? And we'll just quickly go through how this is derived. So the general equation is HA, which leads to hydrogen ions and anions. So A is any anion from the buffer, which is a hydrogen acceptor, HA being your undissociated acid from buffer, which is hydrogen ion donor. Now, by law of mass action at equilibrium, the product of the concentration of dissociates in a chemical reaction divided by concentration of product of reaction, which are constant. So K is equal to HA into anion, okay, and upon HA, where K is your dissociation constant of acid, okay. So then this is the equation you get here, okay. Now we know that pH is equal to log 1 upon hydrogen ion. So when you take reciprocals and the log, so substituting these values, you get log 1 upon H plus ions equal to log 1 upon K plus log A upon HA. Now we also know that log 1 upon K is equal to pK. So now the previous equation can be written as pH is equal to pK log A upon HA. So from this equation, you can see that the buffering capacity of the buffer system is greatest when the amount of anions and undissociated acid is the same, right? Equal to 1 or log A upon HA. So when that happens, then you get pH equal to pK. So what this basically means is that the most effective buffers in the body are those in which the pK value is close to pH in which they operate. Now your isohydric principle, it states that when there is a change in hydrogen ion concentration in ECF, the balance of all the buffer systems changes at the same time. So according to this principle, all the buffers in common solution are in equilibrium with the same hydrogen ion concentration. So this is the equation where K1, K2, K3 are dissociation constants of three acids, A1, A2, A3 are undissociated acids, and A1, A2, A3 are concentration of free negative ions. Now going on to classification of buffer systems. So buffer systems, there are various ways to classify them based on different methods. So one, we can say a bicarbonate versus non-bicarbonate buffers, or ECF versus intracellular buffers, and then we'll talk about some intracellular buffers. So bicarbonate buffers, they form around 53% of buffering of the whole body. Out of this, the plasma bicarbonate contributes 35% and RBC bicarbonate contributes 18%. Now your non-bicarbonate buffers, they form 47% of buffering in the whole body with a contribution from hemoglobin and oxyhemoglobin, then plasma proteins, then organic phosphate and inorganic phosphate. Okay, so this is your non-bicarb buffers. Now coming to extracellular versus intracellular buffers. So here bicarb is a major extracellular buffer which is produced from carbon dioxide and water, and your phosphate is a minor extracellular buffer. It's most important as the urinary buffer. Okay, an excretion of hydrogen as H2PO4 is called as titrable acid. Again, we did this in the last chapter. Then plasma proteins, they form the non-bicarbonate buffer in the blood and are responsible for 7% of the total buffering of blood. Then hemoglobin, even though it is found intracellularly, it is more conveniently regarded as part of the extracellular system. Okay. Now your intracellular buffers, they include organic phosphate, which includes AMP, ADP, ATP, and even your 2,3-DPG. Then proteins of skeletal muscles, and also bicarb present in an intracellular fluid of skeletal and cardiac muscles. Now, which are the major buffer systems of the body? So, you have the bicarbonate buffer, the phosphate buffer, and protein buffer. Okay. So, starting with the bicarb buffer. So, carbonic acid sodium bicarbonate is the most predominant buffer system of ECF, and especially your plasma H2CO3 in the body, which is formed by carbon dioxide and water. We know this reaction now after I think learning about it several times, facilitated by carbonic anhydrase. And this carbonic anhydrase enzyme is present in RBCs, walls of lungs, alveoli, and epithelial cells of renal tubules. Now let's learn about the dynamics of this bicarbonate buffer system. So, carbonic acid dissociates into hydrogen and bicarbonate ions. Now, according to the Henderson-Hasselbalch equation for this system, H2CO3 we know dissociates into hydrogen and bicarb ions. Now, pK for system in ideal solution is less. An amount of hydrochloric H2CO3 is less and hard to measure accurately. Okay, but in the body, H2CO3 is in equilibrium with the carbon dioxide. Okay, hence you can see this reaction that it dissociates back into carbon dioxide and water. Now, if pK is changed into pK1 and carbon dioxide is substituted for H2CO3, pK1 would be 6.1. So, what you get is this equation, pH is equal to 6.10 log HCO3 upon carbon dioxide. Now, since the amount of dissolved carbon dioxide is proportional to partial pressure of CO2 and solubility coefficient of CO2 in millimoles per liter per mmHg is this value 0.0301. So, the clinically relevant form of this equation would be this. Now, bicarb cannot be measured directly, but calculated from values of pH and PCO2, which are measured using pH and PCO2 glass electrodes. Okay. Now, about blood pH and the ratio of bicarb to H2CO3. So, the pH of arterial plasma with a normal carbon dioxide tension of 40 mmHg and normal bicarb concentration of 24 millimole per liter can be calculated from the previous equation. Okay, and when you substitute the values, you get the answer is 7.4. Now the pK1 of this system, which is 6.1, it's still greater than equal to relative to pH of blood, but still this system is one of the most effective buffer systems in body. Why? Because the amount of dissolved carbon dioxide is controlled by respiration and the plasma concentration of bicarb is regulated by kidney. So, through the coordination of these two systems, the pH of ECF is controlled very precisely. Why so? Because this system consists of a weak acid, okay, which easily and partially dissociates into hydrogen and bicarbonate ion. Now, what happens on addition of a strong acid? So, for example, HCl followed by buffering of hydrogen ion by reaction H plus HCO3 will lead to more H2CO3 and more dissociation into carbon dioxide and water. So, the elimination of this carbon dioxide can easily be done through increased respiration or hyperventilation. Okay. Then addition of strong base. So suppose there is sodium hydroxide, it will be converted into a weak base, NaHCO3. NaHCO3 plus H2CO3 will lead to NaHCO3 plus water, which will again dissociate to form sodium ions and bicarb ions. So by this way, the concentration of H2CO3 decreases and that of bicarb increases. So carbon dioxide combines with water again to form new carbonic acid here. So now decrease in carbon dioxide leads to inhibition of respiration. Okay, and that will correct your CO2 deficiency. Whereas increase in bicarbonate ion is corrected by increased renal excretion of bicarbonate ion. So this is sort of the crux of how these two systems operate. Then effective buffering of hydrogen ions. So it's quite evident that at a blood pH of 7.4, the ratio of bicarb to carbonic acid is 20%. So the bicarbonate concentration is much higher, approximately 20 times more than the carbonic acid in blood. So this is referred to the alkali reserve and is responsible for effective buffering of hydrogen ions. Now let's go on to the next buffer system, which is your phosphate buffer system. So now you have an inorganic phosphate orthophosphate buffer system, which is formed by sodium dihydrogen phosphate and disodium hydrogen phosphate, these two, which exist at a plasma pH of 7.4 in a concentration ratio of 1:4. Now, what are the sites of operation of this buffer system? So one is in ECF, that is your plasma and interstitial fluid, where this buffer exists in a small concentration, and so it contributes little to the buffering capacity of plasma. But important thing is that this buffer pair with a pK of 6.8 would be it would have been even more effective buffer than your previous bicarb carbon dioxide system if it were present in an appreciable concentration. Okay. Now in ICF, again this forms an important buffer pair because its concentration in ICF is high, which is 6 millimole per liter, and its pK is 6.8, which is again much closer to the pH of ICF, which is 6.9. Now in another site of its operation is the renal tubule. So in PCT, the tubule, approximately 75% of filtered HPO4 is absorbed. Only 25% of filtered HPO4 is available for buffering in DCT and the collecting duct. So this forms an important extracellular buffer because, why so? Because phosphate becomes greatly concentrated in tubular fluid due to reabsorption of water. We did this last time. And pH of tubular fluid and urine is more acidic than the pH of ECF, which means its pH is quite close to pK of phosphate buffer. So this system is a major elimination route for hydrogen ions via the urine. Now, it's important to know the mechanism of action of this system. So this non-bicarbonate buffer system can buffer both non-carbonic and carbonic acid. It equilibrates as 2H2PO4, which leads to hydrogen ion plus HPO4 ion. Now, on addition of a strong acid, for example HCl, it forms a weak acid. So you can see the equation HCl plus Na2HPO4 will lead to NH2PO4, which is a weak acid, plus sodium chloride. On addition of a strong base like a sodium hydroxide, it forms a weak base. So sodium hydroxide plus NH2PO4 will lead to Na2HPO4, which is a weak acid, plus water. And then you have an organic phosphate buffer system. This was earlier the inorganic buffer system that we talked about. So organic phosphates like ADP, 2,3-DPG, they exist in quantitatively significant amount in the ICF, around 8.4 millimole per liter, giving this compartment the capacity to effectively buffer both non-carbonic and carbonic acid as well as alkalis. Then thirdly, we have the protein buffer system. Okay, this is constituted by your plasma proteins and hemoglobin combined. So buffering capacity of proteins depends on the pK of ionizable groups of amino acids. An imidazole group of histidine with a pK of 6.7 is the most effective contributor of protein buffers. Now your plasma protein buffer system, it accounts for 15% of buffering capacity, and it is effective. These are effective buffers as both their free carboxyl and free amino groups. So these two groups dissociate. Okay. Again, this is Henderson-Hasselbalch equation. So your NH3 splits into NH2 and hydrogen ions. And then this is your pH. So now due to their amphoteric nature, the plasma proteins combine with acids and bases as. So one in acidic pH, the NH2 group of proteins acts as base, accepts proton and gets converted into NH3. In alkaline pH, the COOH group of proteins acts as acid and can donate proton and thus become COO. At normal pH of blood, proteins act as acids and they combine with cations, mainly sodium. Now about the hemoglobin buffer system. So this accounts for 35% of total buffering capacity, and mainly it buffers fixed acids and does transport of gases. Like we know, oxygen and carbon dioxide transported by hemoglobin. Now hemoglobin in intracellular compartment versus extracellular. So hemoglobin, even though is found intracellularly mainly, it's regarded as part of extracellular system, as the hemoglobin is confined to RBCs, which is a cellular component of ECF. So this is the reason why earlier also we referred to it more of like a ECF buffer. And hemoglobin is readily available for buffering of extracellular acids and primary non-carbonate buffer of the body. The buffering system in hemoglobin is provided by dissociation of imidazole group of histidine residues, and hemoglobin is a major buffer in blood. Between a pH of 7 to 7.7, it contributes relatively less to the buffering capacity. Now, due to deoxyhemoglobin being a better buffer than HbO2, as imidazole groups of hemoglobin dissociate less than those of HbO2, making hemoglobin a weaker acid. Also, your hemoglobin molecules, they are present in large amounts. In fact, 1 liter of whole blood contains about 150 grams of hemoglobin, and hemoglobin molecules contain around 38 histidine residues. Now let's go on to the respiratory mechanism for pH regulation. So this is very important now. We know already it's a second line of defense and a short-term control, right? And it acts through the respiratory center located in medulla to regulate removal of carbon dioxide and therefore that of carbonic acid, H2CO3. Now, what is the role of respiratory centers here? So, respiratory centers are influenced by both carbon dioxide as well as hydrogen ions through the central and peripheral chemoreceptors. So respiratory response occurs in response to metabolic acid-base disorders only. And what does that respiratory response consist of? So one, hyperventilation. That will occur in response to metabolic acidosis and results in decreased PCO2 to match decreased bicarbonate ion. And the other respiratory response is hypoventilation, which occurs in response to metabolic alkalosis and results in increased PCO2 to match increased bicarbonate ion. So this is the renal mechanism for pH regulation, and we have already gone through this in the last chapter. So it consists of reabsorption of filtered bicarb, generation of new bicarb, and H plus ion excretion in form of titrable acid and ammonium. Now this is your main part of the chapter, so I would suggest that we all become extra alert here. So coming to acid-base disorders. What is acidosis? Acidosis refers to decrease in blood pH, and alkalosis is its opposite, increase in blood pH. And the acid-base disorders can be classified into two groups: the simple acid-base disorders and the mixed acid-base disorders. So your simple acid-base disorders include metabolic acidosis, metabolic alkalosis, respiratory acidosis, and respiratory alkalosis. And your mixed acid-base disorders include metabolic acidosis and respiratory acidosis, both happening together, or a situation of metabolic alkalosis and respiratory alkalosis occurring together. Now we'll go through these one by one, and this is a very important topic. This is the main topic of this unit, and you also get a short note on, you can get a short note on any kind of simple acid-base disorder, okay? Maybe a metabolic alkalosis or an acidosis or any of them, and where you will need to state that what is the cause, what does it mean, and very importantly, what kind of compensation is expected in that particular acid-base disorder. Will there be a renal compensation? Will there be a respiratory compensation, and how that happens? Okay, so this is really important. So starting with metabolic acidosis, it's a physiological disturbance in which there is either increased net volatile acid load or a increase in loss of base, which is your bicarbonate ion. Okay, what is the primary disturbance? That is decrease in plasma bicarbonate ion, okay, production, which leads to decreased plasma pH. So we need to know the causes of metabolic acidosis. So in what situations can this happen? For example, if there is addition of non-volatile acids to body, that happens in which condition? Like diabetic ketoacidosis, where there may be accumulation of your acetoacetic acid and beta hydroxybutyric acid. Also in a situation of lactic acidosis in hypoxia. Then second can be the loss of non-volatile alkali from body. In what situations can that happen? For example, diarrhea, where you have GI loss of bicarbonate ion, or in type 2 renal tubular acidosis, where you will again have renal loss of bicarbonate ion. The third cause is failure of kidney to basically excrete sufficient net acid to replace the bicarb, which has been used to titrate net daily acid load. Okay, and when does this happen? Like in a situation of chronic renal failure, in which the kidney experiences failure to excrete hydrogen ion as titrable acid and as NH4. And in a situation of type 1 distal renal tubular acidosis, the kidney fails to excrete titrable acid again and NH4. Okay, and so if this metabolic acidosis is uncompensated, okay, then it is characterized by decreased plasma pH and decreased plasma bicarbonate. And this is the equation representing uncompensated metabolic acidosis. Then what will be the compensatory mechanism in this case? So, a basic thing to understand is that when a metabolic acidosis is produced by non-renal factors, the respiratory and renal compensatory mechanisms, they tend to minimize the change in pH of blood. Okay? In renal failure, only a respiratory compensation is possible. So now there are usually two compensatory mechanisms that come into play. One is a respiratory compensation and one is a renal compensation. So increased hydrogen ion stimulates the respiratory center through peripheral chemoreceptors and produces hyperventilation, which is called as your small breathing, which in turn decreases arterial PCO2 value and minimizes degree of acidosis. So the respiratory compensatory mechanism, as I said earlier, is quite prompt, but yes, short term. Okay, and the compensated metabolic acidosis will be characterized by a near normal pH with a PCO2 to compensate the bicarbonate ion. Okay, and this is the equation for that. Now, a renal compensation is slow, but like I said, long-term effective mechanism to control metabolic acidosis. What does it consist of? So increased excretion of fixed hydrogen ions as titrable acid and NH4, increased reabsorption of new bicarbonate, which replenishes the bicarb used in buffering the added fixed hydrogen. And also in chronic metabolic acidosis, an adaptive increase occurs in NH3 synthesis, which helps in the excretion of excess hydrogen ion. Now there is something called as a hyperchloremic metabolic acidosis and a normochloremic metabolic acidosis. So a normochloremic metabolic acidosis is characterized by decreased plasma bicarb and decreased plasma pH with normal serum chloride levels. Okay? This is caused by conditions adding non-volatile acid to the body or due to renal failure to excrete hydrogen ion. Okay? This is your normochloremic metabolic acidosis. What is a hyperchloremic metabolic acidosis? So in that case, there is decreased plasma bicarb and decreased plasma pH, the difference being increase in plasma chloride levels. Here there were normal chloride levels. Okay. Now, which conditions is this caused in? Diarrhea, for example, in which bicarb is lost from gut in exchange of chloride. And another example is type 2 renal tubular acidosis, in which there is failure to reabsorb bicarb by kidneys, and that is accompanied by increased reabsorption of a very high reabsorption of chloride ions. Now, again, an important topic. You can be asked in exams about what is an anion gap. Okay, so this concept of anion gap, basically, it helps us to differentiate between hyperchloremic metabolic acidosis and a normochloremic metabolic acidosis. Now, your law of electroneutrality, it states that total concentration of cations and anions in serum is equal. Now, the routine serum electrolyte determination that we do, it measures all the cations, but only a fraction of anions. So this disparity basically between the total cation concentration and total anion concentration is called as anion gap. So have a look at this figure, which is trying to explain the concept of anion gap. Okay, we'll come to all the parts one by one. So your anion gap basically is a virtual measurement, and it doesn't represent any specific ionic constituent. Okay, so basically we have sodium, potassium, calcium and magnesium. Their total concentration as per your law of electroneutrality should be total concentration of cations and anions in serum is equal. So the concentration of these cations should be equal to that of sum of bicarb, chloride plus any unmeasured anions. Okay, so anion gap would be the concentration of cations minus the concentration of anions, right? Okay, have a look here. So this is your compartment showing all the cations, okay, and this is showing your bicarb, chloride and unmeasured anions. Okay, then anion gap is calculated with sodium being the major cation, but your potassium, calcium, magnesium, they have very small contribution. So this equation effectively becomes anion gap equal to sodium minus bicarb plus chloride. This is your main equation now. So when you substitute their values, okay, you get 12 milliequivalent per liter. Okay. So the normal value of anion gap is 8 to 12 milliequivalent per liter, and it basically reflects concentration of those anions which are present but not determined routinely. Now here, if you look at this equation here, they have removed these ones which we said are quite present in insignificant quantities. So this is this equation B figure, okay, this one. Now this value, it reflects concentration of those anions which are present but they are not routinely determined, except bicarb and chloride, okay, and they include polyanionic plasma proteins also, like albumin, inorganic phosphates, sulfate and ions of organic acids. Now what is the implication of anion gap in metabolic acidosis? So in metabolic acidosis, the serum bicarb decreases as it is utilized in buffering the fixed acid. So now for electroneutrality, concentration of another anion must increase to replace bicarb, don't you think? So that could be chloride or any unmeasured anion, which will constitute your anion gap. Okay. Two, basically what happened? Bicarb ion decreased, right? For the purpose of buffering. So for electroneutrality, now some anion concentration needs to go up to balance that, and that can be either chloride or any unmeasured anion. So now this figure is showing your normochloremic metabolic acidosis, okay, where unmeasured anions concentration increases to replace the bicarb, forming a high anion gap. Sorry, here. Okay, so this is your anion gap, and to replace the decreasing bicarb, sodium ion concentration has increased. This is your normochloremic metabolic acidosis. But in case of hyperchloremic metabolic acidosis, sorry, the chloride concentration will go up further to replace the bicarb. Okay? Here. So this is your situation in hyperchloremic metabolic acidosis. Okay? All right. Now, metabolic alkalosis. So, what is the physiological disturbance? That is either addition of non-volatile alkali or loss of hydrogen from the body. Okay, so the primary disturbance is increased plasma bicarbonate producing a high plasma pH. What are the causes? What are the causes? So, addition of non-volatile alkali to body, that is ingestion of antacids. Then there can be volume contraction alkalosis. We read about this last time because of hemorrhage or thiazide diuretics. Then there may be loss of hydrogen from the body, commonly which happens in vomiting when your hydrogen ion is lost from the stomach. And hyperaldosteronism, where there is increased hydrogen ion secretion by the distal tubules. So your uncompensated metabolic alkalosis will be characterized by increased plasma pH and increased plasma bicarb, and expressed in this equation. Now, what compensatory mechanisms come into play in case of a metabolic alkalosis? So there is respiratory compensation and renal. In respiratory compensation, the pH will increase or there'll be decrease in hydrogen ion by the inhibition of respiratory center through the peripheral chemoreceptors, and this will produce hypoventilation, which in turn will elevate PCO2 and help in normalizing the plasma pH. And compensated metabolic alkalosis is characterized by near normal pH with CO2 to compensate bicarb. This is the equation for that. And the magnitude of respiratory compensation is limited by the fact that hypoventilation results in decreased arterial PO2, which further stimulates respiratory centers via peripheral chemoreceptors. So it's this process cannot go on endlessly, right? Hypoventilation cannot continue endlessly because as soon as there is decrease in arterial PO2, it will stimulate your respiratory centers via peripheral chemoreceptors and counter this process. Now the renal compensation for this. So there is decreased hydrogen secretion by renal tubules and increased bicarb excretion as filtered load of bicarb increases is more than the ability of renal tubules to reabsorb it. So urinary loss of bicarbonate occurs, which leads to decrease in the plasma levels of bicarb, and this helps in restoring pH to near normal. Now what happens in case of respiratory acidosis? So the primary disturbance is increased PCO2, which by mass action causes increase in hydrogen and decrease in blood pH. So the cause is PCO2 increase due to decreased gas exchange across alveoli. In what conditions can this happen? If there is a drug-induced depression of the respiratory centers by opiates or sedatives or anesthetics, if there is weakening of respiratory muscles as happens in Guillain-Barré syndrome, in polio, amyotrophic lateral sclerosis and multiple sclerosis, airway obstruction, impaired gas diffusion, which can happen in cardiovascular or lung diseases. Your COPD is a common example of lung diseases in which there is impaired gas diffusion. And uncompensated respiratory acidosis is characterized by decreased plasma pH and increased PCO2, shown by this equation. Now, there is no respiratory compensatory mechanism for respiratory acidosis. Okay, so buffering in respiratory acidosis, in contrast to metabolic acidosis, almost occurs entirely in the intracellular compartment. So in this case, there will be renal compensation. So increased PCO2 supplies more hydrogen to renal tubule cells for secretion. That will lead to increased secretion of hydrogen as titrable acid and NH3, and increased reabsorption of new bicarb. These will result in increase of serum bicarb to help normalize pH. So, acidosis is mostly but not completely compensated by renal mechanism. Now, compensated respiratory acidosis will be characterized by near normal pH with increase in plasma bicarb to compensate the increased PCO2 and expressed by this equation. Then you have respiratory alkalosis, where your primary disturbances decreased PCO2, which is associated with decrease in hydrogen ion and thus increase in plasma pH. So what are the causes? PCO2 decrease will occur due to increased gas exchange in lungs because of increased ventilation. What conditions do you see increased ventilation? Pneumonia, pulmonary embolus, okay? Secondary to, in this ventilation rate is increased secondary to hypoxemia. Then high altitude, where again ventilation rate is increased secondary to hypoxemia. Even psychogenic hyperventilation occurs when one has anxiety or fear, and in case of salicylate intoxication due to direct stimulation of medullary respiratory centers. Uncompensated respiratory alkalosis will be characterized by increase in plasma pH and decrease in PCO2 and expressed as this equation. So again, as was the case in respiratory acidosis, there is no respiratory compensation for respiratory alkalosis. So buffering in respiratory alkalosis, in contrast to metabolic alkalosis, again occurs entirely in the intracellular compartment. So you have only the option of renal compensation in this case. So there will be decreased PCO2 causing a deficit of hydrogen ions in renal cells for secretion. That leads to decrease in excretion of hydrogen as titrable acid and NH4, decrease in reabsorption of new bicarbonate ion, decrease in reabsorption of filtered bicarbonate. All these result in basically end up decreasing serum HCO3 and help to normalize pH. So in this way, alkalosis is also mostly but not completely compensated by renal mechanism. And in case of compensated respiratory alkalosis, it is characterized by near normal pH with decrease in plasma bicarbonate to compensate decreased PCO2 by this equation. So this table is extremely important and it summarizes all the characteristics of the simple acid-base disorders we talked about. Okay. If you know this table, then I would say you're quite sorted on this topic. You need to know the primary disturbance in each, the range of pH, how does it vary? Same for values of bicarb, PCO2, okay, and what kind of compensation occurs in each of these. So this is very important. Now, this is the point where I want all of you to wake up and become alert back to the lecture. This is a 3-step approach for analysis of acid-base disorders. So when you are either sitting for your PG entrance, you will get numericals which you will solve on basis of these steps. And even when you work as clinicians and you take a blood sample for analysis of acid-base disorder, these are the steps you will follow. So what is the first step? You have taken a blood sample and you will first look at the pH value, okay, to know whether there is acidosis or there is alkalosis. So We know acidosis means a pH value less than 7.4. Alkalosis means a pH value more than 7.4. Then step 2 is where you try to detect that what is the primary disturbance, okay, to understand whether this, so suppose we have reached to this step looking at the pH. Now we want to understand, okay, it is acidosis, but is it metabolic acidosis or is it respiratory acidosis? And the way to know that is to understand what is the primary disturbance. Okay, is it a primary disturbance of bicarbonate ions or is it a primary disturbance of PCO2? Okay, so, and then the third step is when we do analysis of the compensatory response, again from values of plasma bicarb and PCO2. So we, first of all, we know it is acidosis or alkalosis, then we know what kind of acidosis or alkalosis. Once we know that, we need to understand, okay, is there compensation happening? If yes, what kind of compensation is happening? So this is what you deduce from a 3-step approach. Now, to just cement this concept, I thought we could go through some examples. So, I would really appreciate if you all can participate at this point. If you can even speak out the answers if you know them. Please go ahead. Please unmute yourselves and go ahead. So, one example that we can start with is, for example, you get a pH of 7.3 from your arterial blood sample. So, where does that lead us? Acidosis or alkalosis? So, 7.3 less than 7.4 would be acidosis. Next step, what you can do is look at the bicarbonate ions. So, if I tell you that the bicarbonate ions in this sample are 19, so which direction are we going into? So, bicarb less than 24 milliequivalent per liter would lead us to metabolic acidosis. So, the primary disturbance here is that of bicarbonate ions. We've understood that, and we are now saying that this looks like metabolic acidosis. Now, another value given to you is PCO2 being, let's say, 27. So what do you make of that? So that means that the PCO2 is the less value of PCO2 lesser than 40 is actually leading you to towards compensation, towards alkalosis. So actually the less value of PCO2 is trying to correct the acidosis by compensating. And this is being done by the respiratory compensation. Okay, so the answer to this question would be that this is a case of metabolic acidosis, okay, with respiratory compensation. Let's go to example number 2. So if I say now that the pH is 6, let's say 7.6. So where are we heading? We are heading towards alkalosis. Okay. Now I give you two values that bicarbonate is, let's say, 30 and PCO2 is 42. So if you look at bicarb first, it is more than 24. So this looks like a case of metabolic alkalosis. Yes. And now your PCO2 is 42. Okay. So this is taking the situation towards acidosis, isn't it? So basically it's trying to correct the alkalosis. It's trying to compensate. And so we can say that this looks like a case of metabolic alkalosis with respiratory compensation. Here, because the PCO2 value of 42 is taking it towards acidosis or trying to compensate. Okay. Then example 3. Now if I say pH is 7.2. Okay. So again we are looking at acidosis. Okay. Now if I tell you that in this case the bicarb value is 30. Okay. And I tell you that a PCO2 value is 46. Now if you see, as per this table, a bicarb of 30 cannot be the primary disturbance leading you to acidosis. So that means, what is the culprit? The increased PCO2 of what I just said, let's say 46. So that will be your primary disturbance. Okay. That leads us to this being a case of respiratory acidosis. Okay. Now understand that when there is metabolic acidosis, there will be a respiratory compensation. Whenever there'll be respiratory acidosis, there'll be a renal compensation. This is something you can take for granted. So here we are expecting renal compensation. Yes. And how do we know that? How do we confirm that? Because I gave you a bicarb value of 30. So here the bicarb value is increased more than 24 because it is trying to compensate. Okay. So this is a case of respiratory acidosis with renal compensation. Next example, if we say now a pH of 7.7. So we are automatically looking at alkalosis. Now if I give you a bicarb value of 22, okay, and a PCO2 of 26. So what do you think is the primary disturbance now? So if you see a bicarb value less than 24, which is, I give you 22, it can't be the primary disturbance here. Okay. So most likely the primary disturbance is a lower PCO2, which is your 26, which I gave you. So that low PCO2 is leading to respiratory alkalosis. And now how do we comment on what kind of compensation is happening? So we are expecting there's either a renal compensation or not, right? So how do we know? Now we look at again bicarb. I gave you the value of 22. Okay. So yes, bicarb is less because it is trying to compensate. Okay. It is trying to take it towards acidosis and therefore trying to compensate. So we can say this is a case of respiratory alkalosis with renal compensation. Now next example. If I give you a pH of 7.2, so by now you would know, okay, yes, we are talking about acidosis. Now if I give you a value of bicarbonate 20 and a PCO2 of 66. So what do you think is happening here? Can you pinpoint a primary disturbance here? So we can't. Why? Because both your values, bicarb is also less than 24, PCO2 is more than 40. Both are leading to acidosis. So in this case, we call it as a mixed acid-base disorder. That means it is characterized by metabolic acidosis and respiratory acidosis. And now in this mixed case, this is uncompensated. There is no compensation happening in this case, in mixed disorders. Okay? Now, another example. If pH is 7.6 and I tell you that bicarbonate is 32 and PCO2 is 24. Do we know what is the primary disturbance here? No, again we can't say because two things are operating together. So your bicarbonate ion is also increased, leading to metabolic acidosis. Your PCO2 is decreased, leading to respiratory alkalosis. So once again, this is a mixed disorder, okay, consisting of metabolic alkalosis plus respiratory alkalosis. It's hard to say what was the primary disturbance. There are various formulas to calculate those, but that is at a very higher level, not relevant to you right now. And as in case of any mixed acid-base disorder, we will call this uncompensated or no compensation. Now, one last example before we move on. This one, I am talking about this one because I want to just reinforce the anion gap concept that we talked about. So if I tell you that the pH now is 7, so we are definitely looking at acidosis. Okay, and remember your anion gap concept, again we are going to apply it to acidosis, okay, and especially metabolic acidosis. So now I tell you that bicarbonate ion is 14, okay, and PCO2 is 22. So we know the primary disturbance being bicarbonate less than 24. So we say, okay, this is metabolic acidosis. Now your PCO2 is less than 40. I said 22. So there is renal compensation happening. So respiratory compensation happening. So this looks like a case of metabolic acidosis with respiratory compensation. Now in this kind of a numerical, you can get values of ions, okay, when you need to be calculating an ion gap. So in that case, often you can be given let's say the value of sodium ion, potassium ion, bicarb ion and chloride ion. Okay, so how will you calculate an ion gap? Let's go back to an ion gap and see here. So the equation is either cations, all these cations minus anion. So whatever values you have here, you can substitute. Like here I have the value of sodium being 120, potassium being 25. These are not usually calculated or given, so forget these. So the sum of these two minus bicarb, I have a value of 14, and chloride I have a value of 95. So sum of cations minus sum of anions is 122.5 minus 109, which is 13.5. Now I told you the normal value is 8 to 12 milliequivalent per liter of an ion gap. So we have a cutoff of 12 milliequivalent per liter to classify metabolic acidosis as either high anion gap metabolic acidosis or normal anion gap metabolic acidosis. So those, when you get an anion gap of more than 12, you will classify it as high anion gap metabolic acidosis, also called as HAGMA, H-A-G-M-A. Okay, and when it is less than 12, you will categorize it as normal anion gap metabolic acidosis, also called as NAGMA. Okay, and these two have different causes, and basically what a high anion gap metabolic acidosis means that there are other unmeasured anions in the ECF other than chloride and bicarbonate ion. So this is how your anion gap concept comes into play. Okay, I hope you all have got some clarity of the three-step approach which we use for analyzing the acid-base disorders. Now, another important aspect is an acid-base normogram. Okay, this is basically an graphic. It's a graphic analysis of changes in pH, PCO2, and HCO3. Okay, so what all do you have here? This is your arterial plasma bicarb. This is your pH, and this is your PCO2, this L-shaped representation. Okay, so a nomogram is useful in predicting compensatory responses basically to simple acid-base disorders, and these shaded areas, they show 95% confidence limits for normal compensation in simple disturbances. So that doesn't mean that we are ruling out mixed disorders, but this nomogram is basically helping us to understand what kind of compensation is happening for the simple disorders. Okay? And the shifts in bicarb and pH, they can tell us about whether the acidosis or the alkalosis is acute or chronic. So just have a look here. Now suppose you get another numerical or a condition which says that the pH is decreasing less than, so this is your normal, right? 7.4. So this side is acidosis, and when it increases, it is alkalosis, right? So just by looking at this graph, you can tell that when the pH is decreasing, okay, and the bicarb HCO3 value is also less, we are looking at metabolic acidosis. Okay, and for respiratory acidosis, we will look at two values again, one being PCO2 and other being the bicarbonate. Okay, so here if you see, there is the PCO2 values here, they correspond to the respiratory acidosis here. Okay, and this is your bicarb. Okay, now in case of how to differentiate between the acute and chronic acidosis, so between these two, if you see, for acute acidosis, your PCO2 values are quite high because it's an acute situation. Okay, and let's say your bicarb is around, let's say 35, 36. Okay, what happens in case of chronic? So in chronic, first of all, your PCO2 values are somewhat lesser. Okay, and your bicarb has gone up further. Why? Why do you think that has happened? Because it is trying to compensate. Okay, it's taking it towards alkalosis to compensate for the acidosis. So basically, there is very minimal compensation in case of acute respiratory acidosis. That's why your values of bicarb are less, and here they have gone up in trying to compensate for chronic respiratory acidosis. So chronic condition has been there for many years, right? So the body has been able to operate compensatory measures to counter it, okay, unlike a acute situation. Now let's go on to alkalosis. So again, for metabolic alkalosis, the pH will increase, right? And so will your bicarb values, right? That is classic case of metabolic alkalosis. Now here for respiratory alkalosis, we'll see the PCO2 values, right? And you can look at the bicarb value. So here, what do you see? Now again, it helps you see the difference between acute and chronic respiratory alkalosis. So for acute, the PCO2 values are higher, let's say around 17 or so, and the bicarb values are around, let's say 25, 26. Okay, 20, near about 24. And in case of chronic respiratory alkalosis, the PCO2 values are lesser, right? Around 10 if you see, or less than 10. And the bicarb value has gone down. It is far lesser than acute. Why? In trying to compensate. Because the chronic process means, again, it's been there for a long time and the body has been trying to compensate. And so the value of bicarb has gone down towards acidosis to compensate for this alkalosis. So this is how a acid-base nomogram helps us to understand, that what situation are we coming across? Is it acidosis? Is it alkalosis? And whether it is showing acute or chronic pattern. Then another important diagram is Davenport diagram. So this is the graphic display of plasma pH, bicarb and PCO2 in uncompensated and compensated metabolic acidosis and alkalosis. Okay, so it shows you the relation between pH and HCO3 at a constant PCO2. This is your PCO2 isobar. That means this line, any point on this line has a constant PCO2 value of 40 mmHg. Okay, and any AB imbalances, they deter the graph with reference to intercept of PCO2 isobar of 40. This is your CND, and normal buffer line is your ANB. Okay, and where these two intercept is this point N, okay, which is basically at a pH of 7.4. Okay, so if you see, this is your abscissa and ordinate, and they are corresponding to the normal bicarb value of 24 millimoles per liter. So this point N is your triple intercept. Okay, this defines pH, HCO3 and PCO2 of true arterial plasma of any normal individual. Now have a look at this. So again, this can help you understand the concept. Okay, so let's say that if the PCO2 isobar is at 40, then this way, let's say that the PCO2 is increasing approximately to 60 mmHg, and here let's say it is around 25 mmHg. Okay, so what do you think will happen if we move from point N towards A? Just look at the graph and try to understand. So at N, the pH was 7.4, which is normal. Now we are going towards left side. So pH is decreasing, yes. So we are definitely looking at acidosis. Now, what is happening to PCO2 value? It's increasing. It's more than 40, as we had seen in the 3-step analysis. So this is leading to acidosis. So this looks like the primary disturbance causing the acidosis. Why? Because see, your your bicarbonate ion is above 25, right? So this is not the one leading to acidosis. For acidosis, it has to be less than 24. So this is your primary disturbance. So we can just look at it and conclude that this is a case of respiratory acidosis, right? And now if you again observe the um, so respiratory acidosis means there is either a renal compensation or not. Now, how do we know that there is, what is the situation with that? So again, look at bicarb ions. They are going towards, they are above 25, right? That means they are taking this towards alkalosis. They're trying to counter the acidosis. So yes, in this case, there is renal compensation. Okay. Now look at the shift from N to B. What is happening here? So from normal C, normal pH, you are going towards increased pH. So definitely a case of alkalosis. Yes. Now look at uh, PCO2. Okay, PCO2 is becoming lesser than 40. Yes, it's going towards 25 in fact. So this is moving towards alkalosis. And where is your bicarb? Your bicarb ion is way lesser than 24, right? So that is towards acidosis. So bicarb ion can't be the primary disturbance. It's definitely your low PCO2 value. So then this becomes a case of respiratory alkalosis, and it will either have renal compensation or not. Now, again, look at bicarb. So bicarb ion is less than 24. That means it is taking this situation towards acidosis in the process of trying to counter the respiratory alkalosis. So yes, this is a case of respiratory alkalosis with renal compensation. Okay. Now, if you look at point C, what do you think is happening here? So there is definitely lowering of pH from the normal. So it is acidosis. Okay. The PCO2 value is at 40. So PCO2 is definitely not a culprit for this acidosis. So it has to be, it's not respiratory cause, so it has to be metabolic acidosis, right? Now, is it getting compensated or not? So your PCO2 is at the normal level. So it is certainly not trying to compensate this situation. So then here we will call this as uncompensated metabolic acidosis. Now look at point D. So this is going towards increased pH. So definitely a case of alkalosis. What do you think is the primary disturbance? So look at bicarb ions. They are increased more than 24. And PCO2 is again at normal. So again, we are not looking at respiratory cause. So this is a case of metabolic alkalosis. Now, is PCO2 trying to compensate? No, it's at its normal level, right? It's not above 40 that it would try to compensate. So then this is a case of uncompensated metabolic alkalosis. Look at the shift from N to E. What is happening here? So here, pH is decreasing. Definitely we know it is acidosis. Okay. And now let's look at bicarb levels. So bicarb levels are, let's say 23. Okay. So it's less than 24. So it is taking it to acidosis. Yes. So metabolic acidosis we can see. Yes. Now let's look at CO2. Okay. So CO2 at this point in this line at this point is 40, and here it is increasing as we move from N to E. So CO2 is more than 40, so that's also taking it towards acidosis. So this is a mixed case. Okay, the shift from N to E is a mixed disorder where both are causing, there's both respiratory acidosis and metabolic acidosis. Now look at point F. What is happening here? So here your PCO2 we know is 60. It's way above the limit of 40. So it's definitely taking it towards acidosis. But your bicarb ion is not, right? So this is a clear case of respiratory acidosis. What kind of compensation do you expect here? A renal compensation, right? Whether it's there or not, again you can assess looking at your bicarbonate ions that they are greatly increased in trying to counter it and taking it towards alkalosis. So this is a case of respiratory acidosis with renal compensation. Look at point G. What's happening here? Definitely alkalosis. Now PCO2 here is 25. Okay. And what is the bicarb level? Somewhat lesser than 15. So bicarb is definitely not the culprit. It is the less value of PCO2. So looks like a case of respiratory alkalosis. So is there a renal compensation or not? How do we know? So your bicarb ion is way lesser than 24 because it is trying to take it towards acidosis, and so it's trying to compensate. So this is a case of respiratory alkalosis with renal compensation. Lastly, point H. What is happening here? Again a case of alkalosis. So PCO2 is 25. Yes. So that might be the culprit of alkalosis, isn't it? Respiratory alkalosis. Let's look at bicarb. Your bicarb is also above 24, isn't it? So that could also be causing the alkalosis. So we can't say which one is the primary disturbance in this case. Both are leading to alkalosis. So this becomes a mixed disorder, okay, with both leading towards alkalosis. Now your last diagram here is one called as Sigurd-Andersen curve normogram. Okay, so this normogram is basically showing a plot of acid-base characteristics in arterial blood, and this is what I'm talking about. And this is helpful in clinical situations. So this normogram has a PCO2, okay, plotted on the vertical axis. You have pH here on the horizontal, and any point to the left of a vertical line through the pH of 7.4. Okay, so any point to the left here, as we have seen earlier also, will show acidosis, and any point to the right will show alkalosis. Then the position of a point above or below the horizontal line through a PCO2 of 40. Okay, so this is your CO2 titration line. Okay, this is the line with your PCO2 40. Okay, so a position of a point above or below this horizontal defines the degree of hypoventilation or hyperventilation. Okay, so now if a solution containing sodium bicarbonate and no buffers is equilibrated with gas mixtures containing various amounts of carbon dioxide, the pH and PCO2 values at equilibrium would fall along the dashed line on the left here. Okay. If buffers are present, the slope of the line would be greater. Okay. And the greater the buffering capacity of the solution, the steeper would be the line. Now for normal blood containing 15 gram of hemoglobin, the CO2, see the CO2 titration line passes through the 15 gram hemoglobin value mark, okay, here. 15 gram per deciliter mark on the hemoglobin scale. And when the hemoglobin content of blood is low, there is significant loss of buffering capacity, and the slope of this CO2 titration line will lessen. Okay. But if the blood contains buffers in addition to hemoglobin, then even the line drawn from 0 point on a hemoglobin scale, even one drawn from here, is steeper in that case. Okay. Now, what do we do? Basically, for clinical use, arterial blood or arterialized capillary blood is drawn anaerobically and its pH is measured. And pH of the same blood after equilibration with each of the two gas mixtures containing different amounts of carbon dioxide are determined. Then the pH values of the known PCO2 levels are plotted and connected to provide the CO2 titration line of that sample, blood sample. Okay. Then the pH blood sample before equilibrium, pH of the blood sample is plotted on this line and PCO2 of the sample is read off the vertical scale. So the standard bicarbonate content of the sample is indicated by a point here at which the CO2 titration line intersects the bicarbonate scale on the PCO2 40 line. So here, this is the point that we are talking about. The standard bicarbonate content is shown by this point. Okay. And the standard bicarbonate is not the actual bicarbonate concentration of the sample, but rather what the bicarbonate concentration would be after elimination of any respiratory component. So basically, it's a measure of alkali reserve of the blood. Only difference is it's measured by determining pH than the total carbon dioxide content of the sample. And so like the alkali reserve, it is an index of degree of metabolic acidosis or alkalosis present. Then there are some additional graduations on the upper curved scale, which are for measuring the buffer base. Okay, buffer base content. The point where CO2 calibration line of the arterial blood sample intersects this scale shows the milliequivalent liter per liter of buffer base. Okay. And this buffer base is actually what? It is the total number of buffer anions that can accept hydrogen ions in blood. So in an individual with 15 gram hemoglobin, the normal value will be 48 milliequivalent per liter. Now the point on the CO2 calibration line, okay, that intersects the lower curved scale. First we were talking about the upper curved scale. Now the lower curved scale indicates the base excess. This one was the buffer base. So this value you need to remember is positive in alkalosis and negative in acidosis. Okay. This is the amount of acid or base that would restore 1 liter of blood to normal acid base composition at a PCO2 of 40 mmHg. Okay. So this is a little bit about Sigard-Anderson normogram, Sigard-Anderson curve normogram. Okay. So this is important to remember. The base excess is positive in alkalosis and negative in acidosis. Okay. Buffer base normal value is 48 milliequivalent per liter. So that's it. I know this was a very exhaustive topic, but also very important. I will end by saying again that you can get a note on any kind of acidosis or alkalosis, where you may be asked, where you may be expected to mention what is its primary disturbance, perhaps even causes, and very importantly, what kind of compensation will be expected in such a case. Then you should know about at least the names of these normograms. You should know the three normograms that I just told you: Sigurd-Anderson curve. We learned about Davenport diagram. This is the Davenport diagram, this one, and acid-base nomogram. You should know about the three-step approach for analysis. I don't think we could have done a more thorough analysis of this. With at least we took around 7 examples, so I hope there is some clarity. And this table is the crux of everything that we spoke about today, so very important. And finally, your anion gap is an important concept, okay, for differentiating between hyperchloremic and normochloraemic metabolic acidosis. You should know this equation, you should know the normal value and the two types, okay. And I also showed you an numerical with how to calculate in case you are given values to calculate an ion gap, and to comment on what kind of metabolic acidosis you are encountering, okay, whether it is normal anion gap metabolic acidosis or high anion gap metabolic acidosis. And what else did I want to say? Yes, Henderson-Hasselbalch equation. Very important that you know this equation at the back of your hand. You wouldn't be asked to derive it, but you need to know it thoroughly, okay? So that's all from me on this chapter. We'll meet next time for the next unit, which is your applied renal physiology and renal function tests, okay? So thank you very much and have a good day.